Today we shall be discussing about computer generation of topological matrices. Now, generation of the matrices BF and QF is quite a formidable task. We have seen how to generate A. Now, A, we started off with a 0 element matrix and then we filled it up with +1 or -1 depending on the interconnections between various elements. Okay. Now for QF it is, if you remember, it is AT inverse into A, AT inverse into A, and BF was unity matrix and AT inverse AL. Okay. Sorry, BF transpose was minus of AT inverse AL and a unity matrix. All right. So, computation of this will require computation of AT inverse. Now, if you are having say 50 or 60 node system, then it is not advisable to go for the inversion of such a matrix, because AT will have the dimension 50 by 50 or 60 by 60. All right. So, if AT equal to 50 by 50, then you can imagine the number of steps of computation and the time involved in the computation will be prohibitive. Computation time is very large. So, we have already discussed about 3 types of elementary matrices. Depending on the 3 types of operations. The operations are interchange of rows, and then multiplication of a row by -1, and the third one was replacement of a row by the sum or difference with other rows. Now, these 3 operations if we carry out, on a unity matrix, we get elementary matrices. I will just make a mention of some of the standard properties, lemma 1 of these elementary matrices, that is, every elementary matrix has an inverse. Which is elementary. Then last time we discussed, I am just repeating the same point once again. The matrix obtained by performing an elementary operation on a matrix F is equal to the product E into F, where E is obtained by performing the same operation on an identity matrix, that is U equal to 1 0 0 0 like that. Say if it is a 4 by 4 matrix, then if we carry out the same operation on this unity matrix, I get an elementary matrix E. So, if I multiply F by E into F will give me the same final product which I get by doing this operation on F directly. So, we discussed about an example last time. Say F was taken as -1 0 0 1 -1 1 0 0. If we take if we have F was taken as -1 -1 0 1 0 0 0 1 and -1, and by an elementary operation, that is if we interchange row 2 and 3, we get this as the final product F dashed. Now, the same thing we can get if I do the same operation on the unity matrix. Say unity matrix is 1 0 0 0 1 0 0 0 1. If we interchange row 2 and 3, it will be 1 0 0 0 0 1 and 0 1 0. You can see if I multiply F by this elementary matrix E1, then that will give me E1 into F, you can verify yourself, will give me the same F dashed. This property we shall be making use of, in generating QF and BF from A. Let us have first of all a matrix A from the informations given about the interconnection of different elements. So, we generate A, and then by the echelon transform we have identified, say, structure like this. It may be 1 2 3 4 5 and so on. Suppose we find something like this. The nodes, the elements which are connecting to the nodes 1 2 3 4 and so on to form a tree will be corresponding to these elements, that is 1, then it may be 3, it may be 4. So, we may have a tree, a possible tree from these interconnections 1 3 4 and maybe 5. There may be more number of nodes, okay, and so on. So, once we have identified the elements of a tree, then we rearrange A. Such that we have 1 3 4 5, these are the nodes, these are the elements corresponding to AT, and rest of it is put separately as a submatrix AL. Okay. A means small a means plus minus 1 or 0. So, we get a non-singular matrix AT, which is a square matrix, all right, which is a square matrix, and we will see from this square matrix, a square matrix which is having a structure like this 1 1 1 1 like this, these are all zeros, and a and so on. So, it is having all the diagonal elements as 1, zeros on the left, and a's which may be plus minus 1 or 0 on the right. Now, if this is our matrix AT, then we reduce this matrix by unitary transform. Let us see, we reduce it by a unitary transform to a unity matrix. We transform this to a unity matrix. Let us see what we get. Let me start with an example first. Let F be a matrix like this, say minus 1 1 0 1 0 minus 1 1 0 minus 1 0 0 0 0 0 0 1. Is it possible to get by these echelon transforms? Is it possible to get a unity matrix here? Let us see. We take the first one, row 1 is negated, then we get 1 minus 1 0 minus 1 0 minus 1 1 0 minus 1 0 0 0 0 0 0 1. So, R1 replaced by minus R1. Then from here R1 plus R3 we substitute for R3, then F2 becomes R1 plus R3 will be replacing R3. So, 1 minus 1 0 minus 1 0 minus 1 1 0, then this plus this is 0, this plus this is minus 1, then 0 minus 1, then 0 0 0 1. Okay. Then replace R2, interchange R2 and R3, R2 and R3 are interchanged. Okay, there will be a shortcut. Let me negate R2 first. R2 is replaced by minus R2, and then we replace R3 by R2 plus R3. Then what we get? F3 will be 1 minus 1 0 minus 1 0. See, R2 is replaced by minus R2. So, this will become 0 1 minus 1 0 0 1 minus 1 0, and then this R2 plus this R3 we replace R3 by this R2 plus R3. So, this will become 0 0 minus 1 minus 1, is it not? See, 0 plus 0, 1 plus minus 1 is 0, then 0 and minus 1 is minus 1, and then minus 1 and 0 becomes minus 1. So, the fourth one is 0 0 0 1. this is F3. Now, we have got almost diagonal elements as unity. If I just change the sign of this, so F4 is 1 minus 1 0 minus 1 0 1 minus 1 0 0 0 1 1 then 0 0 0 1. Now, it is very simple. If I add R1 plus R2 and replace this R1 by this, that is, if I add these two, I get F5 as 1 0 minus 1 minus 1, then 0 1 minus 1 0, then 0 0 1 1 0 0 0 1. Okay. Then F6, it is just a simple manipulation. F6, now if I add row 3 and row 4, say row 3 with row 1, so row 1 is replaced by row 1 plus row 3, then what do I get? 1 0 0 0, then row 2 by row 2 plus row 3, then 0 1 0 1, then 0 0 1 1, then 0 0 0 1, and then F7, it is very simple. R2 minus R4 if I take and replace R2 by that, then I will get this minus this, row 2 minus row 4 is going to replace this. So, what do I get? 0 1 0 0. Similarly, row 3 minus row 4 is going to replace row 3, then what do we get? 0 0 1 0 and then 0 0 0 1. So, I get a unity matrix. So, through these echelon transforms, a square matrix, which is a non-singular matrix, a square matrix can be reduced to a identity matrix through these echelon transforms. Therefore, you can write, let us write these as E L, L minus 1, L minus 2, various steps of these transformations as this. Therefore, on F we have carried out these multiplications at different stages to obtain U, and all these echelon transforms, they have their inverses. So, F can be written as epsilon 1 inverse, epsilon 2 inverse, epsilon L inverse into U, which means epsilon inverse, epsilon 2 inverse, epsilon L inverse. So, the role of the generic F, the role of this generic F is to be played by AT. Therefore, AT will be like this, or AT inverse I can write as this Therefore, what will be Q? QF is EL minus 1 and so on, E2, E1 into A, is it not? Because QF we know is AT inverse A, and AT inverse is obtained by repeated operations like this, elementary operations like this. So, the repeated operations on A will give me QF. AT inverse can be conceived as the product of such elementary operations, such elementary matrices. Okay. So, let us use this, and QF once QF is known, you can calculate from there BF. So, let us consolidate the steps. Step 1, generate the incidence matrix A. Generate any incidence matrix A from the given data. Then step 2, generate a tree by elementary operations. Then step 3, rearrange A, rearrange the columns of A such that A equal to AT partitioned AL. Up to this is very simple, and then on AT we carry out this chain of elementary operations, that is multiplication by various elementary matrices. So, step 4, generate QF from A in step 3. This A, after rearrangement of the columns in step 3, by creating U matrix in this place, by creating U matrix in place of AT by elementary operations. Okay. I hope this point is clear. Once you have followed this, then QF automatically becomes UQL. A gets transformed to QF, and once you have got QF, next compute BF, which is minus QL transpose U. So, we shall take up an example, simple example, and then see how to obtain QF and BF. Suppose the matrix A is given like this: 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 0, 0, 1, 0, minus 1, 0, 1, 0, minus 1, minus 1, 1, 0, 0, 0, 0, 0, 0, minus 1, 0, minus 1, minus 1, minus 1, 1, 0, 0, 0, 1, 0. Suppose this is A. We interchange R4 and R1, and then R1 is multiplied by minus 1. What do we get? A1. Remember, you do not get the same A matrix anymore, it is a transformed matrix. Once you go through these transformations, A is gradually getting transformed to Q. So, do not write A again. I have observed many of you, while carrying out this operation, you just put equal to this. This does not become equal to this. It is a new matrix that you obtain here. So, bear this in mind. So, 1, 2, 3, 4, 1, 0, 0, 0, minus 1, because I have replaced 1 and 4 and then I have negated this. So, 1 minus 1, then 0, 0, 0, minus 1, 0, then 0 minus 1 minus 1, 1, 0, 0, 0, then 0, 0, 0, minus 1, 0, minus 1, minus 1, and then 0, 0, 1, 0, minus 1, 0, 1. So, this is the next matrix that we get. Then from here we multiply row 2 by minus 1. If I multiply row 2 by minus 1, this will become plus 1. Okay, this will be plus 1, this will be minus 1. So, I will get 1, 1 like this, and then if we interchange R3 and R4, this one will come here, this will go here, and then if I change the sign of this, so all these steps, R2 is multiplied by minus 1, R3 and R4 are interchanged, and then in that new R4, if I put a multiplier minus 1, what will be the matrix like? 1 minus 1 0 0 0 minus 1 0, then 0 1 1 minus 1 0 0 0, then 0 0 1 0 minus 1 0 1, and then 0 0 0 1 0 1 1. My interest was to generate first of all unity elements here and then zeros to the left, and then here it can be plus 1 or minus 1 or zeros. This is my partitioned part. Now, R1 plus R2, R1 plus R2, if I add these two and put it in R1 A3, then becomes 1 0 1 minus 1 0 minus 1 0, 0 1 1 minus 1 0 0 0, 0 0 1 0 minus 1 0 1, 0 0 0 1 0 1 1. Okay. Then R1 minus R3, if I take R1 minus R3, so next step we replace R1 minus R3, R1 minus R3 is going to replace R1, then R2 minus R3 is going to replace R2, then what do I get? A4 equal to this minus this, it will be 1, this R1 minus R3, this minus this, so 0 0, then minus 1, then 1 minus 1 minus 1. Okay. Then R2 minus R3, R2 minus R3 will give me 0, 1, 0, minus 1, plus 1, 0, minus 1, then 0, 0, 1, 0, minus 1, 0, 1 and 0, 0, 0, 1, 0, 1, 1. Okay. From here, now we are gradually going to a unity matrix, only these two elements are to be changed. Now, if I add row 4 with this, 1 and minus 1 will make it 0, 1 and minus 1 will make it 0. So, now next operation left is just to add R4 to R1 and R2. So, R1 plus R4 is going to replace R1 and R2 plus R4 is going to replace R2. Then we get A5 equal to 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. On this side you have got 1 0 0 1 1 0 minus 1 0 1 and 0 1 1. And what is this? This is QF. So, you have obtained QF, which is nothing but U, and this side you have got Q link. This is Q link. So, what will be BF? Very simple, minus transpose of this first and then U. That means, if I take transpose of this, it will be 1 minus 1 plus 1, sorry 1 1 minus 1 0 and with a negative sign. So, it will become minus 1 minus 1 1 0, then 0 minus 1 0 minus 1 0 minus 1 0 minus 1, then 0 0 minus 1 minus 1 0 0 minus 1 minus 1, okay. And then unity matrix 1 0 0 0 1 0 0 0 1. So, this is BF. So, it is so simple. From starting from the A matrix, we have got BF and QF by these elementary transformations. So, if you are given an A matrix, first of all through echelon transform you have to find out a possible tree. If you find out a possible tree, then again rearrange the columns, get A, so that you can partition A into AT and AL, and AT is a square matrix which has to be transformed to a unity matrix, and automatically the right hand part, that is the part associated with AL, will also get transformed, which will be generating QL. So, U partitioned QL, this will be the total matrix QL. Okay. We are given a problem, an interesting problem. Take up now. Which of the following AT or AT inverse, which of the following AT or AT inverse submatrices correspond to a tree, correspond to a tree of a network, okay, tree of a graph with 4 nodes. Do you understand the question? Which of the following AT or AT inverse submatrices, which of the following AT or AT inverse submatrices correspond to a tree of graph with 4 nodes. Now, the submatrices are, I will take up one by one. You have to identify which can be a possible case, possible submatrix of a tree. 1 minus 1 0 1. Next 1 0 0 1 1 0 and then 0 0 1. Let us take up one or two at a time. Is this a possible submatrix? Obviously, a 4 node system should have AT of dimension 3 by 3. So, since this is of dimension 2 by 2, this is ruled out. Again this one, let us take up this one. This is a 3 by 3 matrix. So, it could have been a possible case, but here you find both the signs are plus 1 in this column. Now, if you remember, in the A matrix, in each column you will have 1 plus 1 and 1 minus 1 at the most. You cannot have 2 plus 1s or 2 minus 1s. So, this is also ruled out. Let us take up one or two more cases. AT equal to minus 1 0 0 minus 1 1 0 0 0 1. Is it possible to have AT as a submatrix corresponding to these values? See, the determinant is 1. Determinant of AT should be 1 or minus 1. So, here that is satisfied. It is 3 by 3 and you see there is no presence of 2 plus 1s or 2 minus 1s or all zeros. So, this is a possible case. This is a candidate. Let us take another example. AT minus 1 equal to 1 0 0 minus 1 1 1 0 0 0. Is this a possible submatrix of a tree? What would be the determinant of this? There are 3 zeros. So, the determinant is 0. So, inverse of this, that is AT does not exist. AT does not exist. So, this cannot be a candidate. Okay. Let us take another matrix AT equal to 1 0 minus 1 0 0 1 minus 1 0 0 0 1 0 and 0 0 0 1. Can this form a 4 node submatrix of a 4 node system? Obviously, this is a 4 by 4 matrix, and for a 4 node system it should be a 3 by 3 matrix. Therefore, this is also ruled out. Next, AT inverse equal to minus 1 0 0 1 minus 1 minus 1 0 0 1. Now, here the determinant is 1, it is a 3 by 3 matrix, all the elements are either plus or minus 1 or only minus 1 and so on. So, this could be a possible case. Let us see what AT will be like. AT will be, determinant is plus 1. So, we will replace this by the corresponding minus. How much is it? This will be minus 1, this will be replaced by minus 1, this will be replaced by, okay, this will be replaced by 0, then this will be replaced by 0, this will be replaced by 1, then this will be replaced by 0, this will be replaced by 0, this will be replaced by 1, and this will be replaced by 1. Is that so? And then the transpose of this. So, that gives me -1, -1, 0, 0, 1, 0, then 0, 1, 1. Now, once again you will find there are two similar signs in each column. So, this is also ruled out. Okay. Let us take another example, AT equal to 0, 0, -1, -1, 0, 0, 0, 1, 1. Here is the determinant non-zero? Yes, -1, -1, 1. So, determinant is positive 1. It is a 3 by 3 matrix and all other conditions are satisfied. So, this is also a candidate. So, there are two situations, one is this and the other one is this, where AT given by these can form a part of a submatrix, can form a part of a tree. Another question, we will take up another example. The elements of a graph, suppose this is given to you in a tabular form, the branches, I will just write down the problem, starting node and finishing node. Branch 1, starting node 0, finishing node 1. Simultaneously, I will draw the graph. You are asked to draw the graph. So, branch number 1, let us take this as the starting node 0 to 1. So, put the arrow to the finishing node. Then branch number 2 is between 0 and 2. So, between 0 and 2, so let us say this is node 2, direction is like this. Then third one is 0 and 5. So, let us take 0 and 5, this is the third node, 1, 2, 3. Then fourth node is 1 to 2. Fourth node is, fourth branch is between 1 and 2. So, the third is 0 and 5, the fourth element is between 1 and 2, the fifth element is between 1 and 3. So, fifth element is between 1 and 3. Let us take node 3 here, then 1 and 3. This is the fifth element. Then the sixth element is between 3 and 4, between 3 and 4. So, between 3 and 4. So, let us take this as the sixth element. Then seventh element is between 2 and 5, 2 and 5. So, between 2 and 5, seventh element. Eighth element is between 4 and 5, between node 4 and 5, eighth element. And the ninth element is between 3 and 5, between 3 and 5, ninth element. Okay. So, this is the graph, taking O, the 0th node as the reference, taking 0th node as the reference, write a matrix in the ascending order. That is, you take the elements and the nodes in the proper order and then form a tree. So, let us write matrix A. We will take up first element 1. Element 1 is between 0 and 1. So, it is nodes and these are the elements or branches. This is -1 and the reference node is 0. So, I am not showing that 0, 0. How many nodes are there? 1, 2, 3, 4, 5. So, 1, 2, 3, 4, 5. Excluding 0, there are 5 nodes. Element 2 is between 0 and 2. So, 0, -1, 0, 0, 0. Is that all right? Next, element 3 between 0 and 5. So, element 3 is between 0 and 5. 0, 0, 0, 0, -1. Then element 4, if you see element 4, we have taken out 1, 2 and 3. Element 4, if I put, that forms a loop. So, 4 has to be put in the link elements. I am trying to form AT going by order of the elements as they appear without forming a tree. So, element 4 will appear here. Then element 5 if I take, so elements of the links I will put across. Element 5 comes next, that is between 1 and 3, between 1 and 3, 0, 0, 0. Okay. So, element 6, can I have element 6 now? Yes, element 6, that is between 3 and 4, 0, 0, 1, -1, 0. Okay. Element 7 we can have between 3 and 5, but then if I put that, then 1, 5, sorry, element 7 if I put, then 2, 3 and 7 will form a loop. So, element 7 you cannot have here, it has to be put here. Similarly, element 8 if I put, that will also form a loop. So, element 8, 9, 7, they will all have to go there. So, you see 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, it cannot be more than 5 by 5. So, 4, 7, 8, 9 I put in this order. And then number 4, element number 4 was between 1 and 2. So, 1 and 2, 0, 0, 0. Element 7 was between 2 and 5. So, 0, 1, 0, 0, -1. Element 8 was 4 and 5, 0, 0, 0, 1, -1, and element 9 is 3, 5. So, 0, 0, 1, 0, -1. So, this is the matrix A. Now, by transformation of this to a unity matrix, you can generate Q and finally B matrix. Okay. Next time we shall be discussing about image impedance and iterative impedance, and from there we will go to characteristic impedance of symmetric network. Okay. This will be the introduction to classical filter design. So, 2-port network, whatever you have studied earlier, you please brush up whatever you have learnt, so that you can follow this. Thank you very much for a patient hearing. Good morning friends. Today we shall be discussing about image impedance, iterative impedance and finally the characteristic impedance of a two-port network. Characteristic impedance of a two-port network. Now, let us consider a general network having impedances ZA, ZB and ZC. The ports are 1 and 2. Now, image impedance we define image impedance as this. If I load this side by an impedance ZI2, the impedance seen from this side is ZI1, and if I load this same network, I show the network just by a block. If on this side if I put ZI1, then impedance seen from this side is ZI2. Then ZI1 and ZI2 will be the image impedances for this network. So, for a general network where ZA, ZB, ZC are any set of values, ZI1 and ZI2 will be different. So, there are two image impedances. You look into the circuit from this end, if I load on that side ZI2, then the impedance in is ZI1. If I look at the network from this end and if I load it with ZI1, the impedance in is ZI2. Mind you, you cannot have these unique values with any set, you cannot have any combination. So, they are dependent on, these values are dependent on ZA, ZB and ZC. Let us see what will be the relation between ZI1, ZI2 and these element values ZA, ZB and ZC. Now, by definition we have got ZI1, the impedance seen from this side is how much? ZA plus parallel combination of ZC and ZB plus ZI2. ZC in parallel with ZB plus ZI2. Agreed? So, that gives me ZA plus ZC into ZB plus ZI2 divided by ZC plus ZB plus ZI2. Agreed? Similarly, ZI2 will be equal to ZB plus ZC into, just replace A by B, interchange A and B, ZC will be ZA plus ZI1 divided by ZC plus ZA plus ZI1. Agreed? So, let us take once again from definition ZT1, impedance is ZT1. So, ZT1 will be equal to ZA plus parallel combination of ZB plus ZT1 with ZC. Okay. So, ZT1 is equal to ZA plus parallel combination of ZC with ZB plus ZT1, which means ZA plus ZC into ZB plus ZT1 divided by ZC plus ZB plus ZT. If I multiply again, cross multiplication will give me ZT1 squared plus ZT1 into ZC plus ZB on this side. On this side I have got ZA ZC plus ZB plus ZA ZT1 plus ZC ZT1 plus ZC ZB. If I transfer everything on this side, I will get ZT1 squared plus ZT1 into ZC plus ZB minus ZC minus ZA. So, it becomes ZB, ZC will go, so ZB minus ZA. Correct me if I am wrong. Okay. Minus ZA ZC ZA ZC minus ZA ZB minus ZC ZB equal to 0, or I can put all of them as plus. Okay. That is ZT1 squared plus ZT1 into ZB minus ZA minus sigma ZA ZB equal to 0. So, how much is ZT1? If I invert it, so that will be giving me tan hyperbolic p by 2 is equal to ZA by Z naught, or tan hyperbolic p by 2 is ZA by Z naught. Z naught is equal to root over of ZA into ZB. So, that gives me root over of ZA by ZB. Okay. So, we get ZA is equal to Z naught tan hyperbolic p by 2, one may write like this, and ZB equal to cot hyperbolic p by 2. Either way you can write. All right. Okay, we will stop here for today. We will take up some problems in the next class. Thank you very much.